From the precise structural load on a bridge to the aerodynamic friction on a fuselage, physical systems are defined by continuous change. Tracking that change requires the rigorous mindset of a master builder, using specific mathematical schematics to map every movement. This masterclass compiles the technical requirements of Calculus 1, 2, and 3 into a single interconnected framework for modeling the physical world. Mastery involves visualizing equations as structural materials and theorems as physical blueprints. Our dimensional color coding protocol starts with the blue layer, Calculus 1. This stage covers the calculation of instantaneous rates of change in one dimension. The green layer, Calculus 2, introduces the infinite refinement and advanced workarounds needed for more complex functions. The red layer, Calculus 3, expands these mechanics into the multivariable dynamics and three-dimensional vector fields that define real-world environments. Unifying these 3 semesters into a single schematic provides the necessary resolution to analyze the complex systems found in modern physics and engineering. The mathematical limit serves as the foundational mortar for this entire edifice, allowing us to define how a function behaves as it approaches a specific point without ever needing to reach it. We use the limit to derive the core rules of the derivative, such as the power and product rules, which measure the exact rate of change at a specific moment. For functions divided by one another, we use the quotient rule. Recalling the specific structure of this formula, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all over the square of the denominator, is simplified with a mnemonic. The low d high minus high d low, draw the line and square below memory trick ensures a builder can quickly calculate the derivative of a ratio.
To differentiate composite functions, where one function is nested inside another, we apply the chain rule, differentiating the outer layer before multiplying by the derivative of the inner layer. To evaluate the derivative of sine of e to the x squared, we first differentiate the outer sign to get cosine. Next, we address the inner exponential, which results in e to the x squared times the derivative of the final inner layer, 2x. Mastering these derivative rules allows an engineer to isolate and measure exact rates of change at any infinitely small moment in time. Beyond simple rates, we use optimization to determine structural efficiency, finding the points where a system reaches its highest or lowest value. This graph illustrates the process. By identifying the points C and D where the tangent line is perfectly horizontal, we locate the local maximum and minimum values of the function. The mean value theorem, or MVT, guarantees that on a continuous and differentiable interval, there is a specific point where the instantaneous rate of change must equal the average rate of change for the whole interval. We can contrast this with the intermediate value theorem. If a hot air balloon rises from 0 to 100 feet, the IVT says it must have been at 50 feet at some point. The MVT, however, guarantees that if the average ascent was 5 feet per minute, there was at least one moment where the balloon's velocity was exactly 5 feet per minute. Shifting focus to integration, we move from analyzing moments to calculating accumulation, the total sum of infinitely small changes over time. The 1D fundamental theorem of calculus is the mathematical bridge that connects these two operations, proving that differentiation and integration are inverses. The FTC shows that determining the slope of a structure and calculating its total volume are reverse applications of the same core logic. Basic Calculus 1 tools often reach their limits with non-standard functions. This requires the green layer, integration workarounds used to solve more resilient problems. When an integral involves the product of two functions, we use integration by parts, rearranging the formula into uv minus integral v du. We select the variables for this operation using the I-late hierarchy: inverse trig, logarithmic, algebraic, trigonometric, and exponential. Visualizing I-late as a VIP line helps prioritize the selection. Inverse trig functions are the celebrities chosen first for u, while exponential functions are left as the dv. Trigonometric substitution provides a geometric hack for integrals containing radical expressions, allowing us to map algebraic variables onto right triangles to simplify the math. For complex rational functions, we use the demolition method of partial fractions, breaking down unified denominators into simpler, integrable components. Calculus 2 integration relies on recognizing structural patterns to reverse engineer functions that resist basic summation. We now shift from continuous geometry to the management of infinite discrete sequences and series. We employ convergence tests, such as the ratio and comparison tests, to determine if an infinite addition will settle on a finite sum or grow without bound. Taylor and Maclaurin series serve as a cloning mechanism, using these infinite series to replicate complex functions. The formula uses successive derivatives at a center point to stack polynomials, creating a curve that eventually matches the original function perfectly. Expansions for e to the x, sine of x, and cosine of x show added polynomial terms physically warping to match the transcendental waveform. Taylor series allow an engineer to replace a complex, unintegrable curve with a basic, workable polynomial over a specific interval. We now upgrade the dimensional engine to the red layer, Calculus 3. This extrudes flat 2D blueprints into real 3D surfaces, like ellipsoids and hyperboloids. To measure change in this 3D landscape, we use the partial derivative, holding all variables constant except for one to see how the surface slopes in a single direction. The gradient, represented by the nabla symbol, combines these partial derivatives to show the path of the steepest possible ascent on the surface. The nabla operator acts as a high-tech compass, with its needle pointing directly towards the steepest summit of a topographical peak. Using double and triple integrals, we accumulate values across multiple axes to calculate the volume, mass, and center of mass for solid objects. Depending on the object's symmetry, we often shift coordinates from the standard Cartesian system into cylindrical or spherical systems to simplify the integration. Multivariable calculus provides the coordinates and dynamic slopes needed to build and model within three-dimensional space. The most complex applications involve vector fields, which represent dynamic systems like fluid flow, weather patterns, or electromagnetic force. Divergence is the operator used to measure whether a fluid is expanding outward from a microscopic point or compressing inward. Curl measures the rotation or vorticity of that same fluid within the field. Understanding divergence and curl is essential for predicting and modeling any dynamic flowing system. Calculus 3 operates as a high-dimensional extension of the core logic we've established in the first two layers. This synthesis is realized through the grand unified theorems, Stokes, Green's, and the divergence theorem. When we compare the 1D fundamental theorem of calculus to these 3D vector theorems, we see a shared structural logic. Regardless of the dimension, these theorems all relate the behavior of a boundary to the contents of the interior space it encloses. You have now reviewed the complete blueprints of change and accumulation across all 3 semesters. Mastering these integrated tools provides the structural formulas used to model and optimize continuous systems across physics and the mechanical world.